Hey everyone, welcome to the video lectures for section 2.7 and chapter 8 kind of all smushed together. So in this section we'll be talking about numerical methods for doing differential equations. So the idea is, well, what happens if we can't solve the equation analytically? What if it just doesn't work? We can't solve it, there's no formula for it, we end up with some nasty integral that we don't want to evaluate. How do we go about solving it? And the one way we can do that is by using numerical methods. So we're talking about a couple methods in this section that we can use to solve these equations. So let's go ahead and start with the simplest one, Euler's method. So first thing we're talking about is Euler's method for numerically solving differential equations. And the idea for Euler's method is as follows. So for a first order equation, we have the formula set up where we have dy dt equals some function f of t and y. Now, if we're looking at the curve that's going to be our solution to this, dy dt should be something like a tangent line slope, right? Dy dt is the slope of the tangent line. So one thing we think to do is just use tangent line approximations to our solution curve at every point and just keep stepping forward in time and see what we get. So our goal is just to kind of stitch these little tiny tangent lines together and piece together the curve as we move forward. So let's say we're going to start somewhere. So let's start at some point t0, y0 corresponding to initial condition. If I wanted to approximate the function y at some t1 bigger than t0, but not too big, just slightly bigger than t0, I could do that by a tangent line approximation. What would that entail? That would entail saying that y of t1 is approximately equal to y at t0 plus the derivative at t0 times t1 minus t0. This would be my tangent line approximation to this curve. So what we're going to do is we're going to call this right-hand side y1. So we're going to set y1 equal to y0, which is this point, plus dy dt at t0. But what is dy dt? Dy dt is just f. So this would be f at t0, y0 times t1 minus t0. So this gives us a way to calculate what an approximate next point would be on our curve at time t1. So we have an approximate equality here. And then the thought is we can just keep iterating this forward and forward and forward and just keep moving to get more and further down in time. And the thought is that if t1 minus t0 is small, this should be a good approximation. We'll talk about what we mean by that in the next couple of videos, but if it's small enough, then the tangent line should be relatively close to the actual slope, and it shouldn't be too far off as we move down through the curve. Now what we want to do to get solutions for larger times is we want to iterate this. So iterate this process to get the solution at later times. Now the main issue here we have is that, so for the first step, we know we're starting at the right spot, right? We assumed that we were starting at y0, t0, y0. We have a point, we know we're starting at the right spot. But now for our second step, all we have is this y1. We don't know what y of t1 was supposed to be. All we have is y1. So for the second step, we're getting y2 is going to be y1 plus f of t1, y1 times t2 minus t1. But here we didn't know if our actual solution is supposed to hit t1, y1. So we might be off by a little bit more than we were before because we've now done this process twice. So whether or not this method stays close to our actual solution depends a lot on the ODE itself. So whether or not this process stays close to the solution depends on f and the initial condition. A way to sort of look at this, if you look in the examples in the book, examples 1 and 2 stay close as you iterate, but example 3 does not. And that's because for 1 and 2, the solutions are converging to a point. So if you're close, you're sort of still going to be nearby. But for exercise 3, since everything's diverging, if you end up off your solution curve, you're going to end up further away and further away down the line because all your curves are spreading out instead of coming in together. Because basically, because we don't know what y of t1 is supposed to be, we're starting from approximation, we're effectively jumping onto a different solution curve, right? If you think of the plane is just filled with these curves that are the solutions, when I don't hit the solution exactly right and jump to something nearby, I end up on a slightly different curve. And as long as those curves are all going to stay close together as time goes on, we're fine, it doesn't matter. But if those solutions are diverging as time goes on, then we're going to be in trouble, and we're going to end up far away from our solution. So over the course of this chapter, in this section, we're going to look at a couple different examples of what we can do to model these types of problems. But example 3 is always going to be an issue because you can never be exactly right. And it's always going to be an issue that when you try to approximate, you're going to end up on a different curve, and it's going to run you further away as time goes on. So example 3 is always going to be an issue, but we're talking about different ways we can do slightly better than just this simple, tangent line approximation to try to calculate the solution to our equation. All right, that's it for this video. In the rest of videos, we'll talk about more improved methods and more things like that, but we'll get onto those when we get there. Thanks a lot for watching, and I'll see you in the next one.